Hello students, this is lecture 6 of MTH 201. In the last lecture we discussed paths and curves in the plane and in space, and we also looked at the motion of a particle using these concepts of paths and curves. So today we are going to first talk about quadric surfaces. A quadric surface is the graph of a second degree equation in three variables x, y and z. The general form of a quadric surface is ax square plus by square plus cz square plus dx times y plus ey times z plus fz times x plus gx plus hy plus iz plus j equal to 0. So this is an equation. You see three variables x, y and z, and all the terms a, b, c, d, e, f, g, h, I, j are all constants. They are all real numbers. So why is it called a quadric surface? Because the highest degree that you see of a variable is 2. So if you look at this equation, you see that, so if you have three variables, x, y and z, what are the 2 degree terms that you can have? You can either have squares of x, y, z or their products, right? And if you have three variables and you take two products of 2, you get three terms, right? X, y, y, z, z, x. Then there are linear terms, degree 1 terms, which are x, y, z, right? And then there is a constant term. So you have seen polynomial of degree 2, right, in one variable. This is, you should think of it as a polynomial of degree 2 in three variables now, right? And I'm writing it as an equation. So when you write it as an equation, you get a function. So you get an equation in terms of x, y, z, right? And if you look at all the values of x, y, z which satisfy this equation, that is the graph of this function and it's called quadric surface. We'll come to pictures and then it will be clear what we mean by this. Quadric surfaces are generalization of conic sections. What are conic sections? They are circle, ellipse. So circle is a particular case of ellipse when major and minor axes are equal. Parabola, hyperbola, which are all obtained by intersecting a cone with a plane, right? That is why they are called conic sections. So these surfaces are generalizations of those conic sections. All these conic sections are in R2, right? We draw them in a plane. Whereas we draw a quadric surface in R3. We draw it in space. Okay, because there are three variables. So this general form can be reduced to one of the two standard forms by translating the surface or rotating the surface. Okay. And what are the two standard forms that you get? One is where you just see squares of each of the variables, right? And constant. So you don't see any cross terms or linear terms. The second one is interesting where you have squares of x and y and z comes as a linear term and there is no constant. Okay, so that is another version that you get, another standard form that you get. Okay, so now let us define what a cylinder is. Okay, so if one of the variables x, y or z is missing from the equation, then the surface is called a cylinder. See, when I say that one of the variables is missing, it doesn't mean that you are looking at a surface in R2 now. You are still looking at it in R3. It's just that one of the variables is missing and then you draw the graph of the equation that you get. Okay, we will look at examples of cylinders in a minute. Now, this is a method that can be used to sketch a quadric surface. In order to sketch a quadric surface, it is useful to determine the curves of intersection of the surface with planes parallel to the coordinate planes xy, yz and zx. So what are coordinate planes? This we saw in the first week. XY plane means all the collection of all the points where Z is 0. YZ means collection of all the points in R3 where X is 0. ZX means collection of all the points in R3 where Y is 0. Okay. So that gives you planes. And when you intersect these equations with these planes, you get curves on that plane. So you draw those curves and then you determine what the full surface should be. So you just don't do it for coordinate planes, you do it for any plane which is parallel to the coordinate plane. For example, if you have xy plane that is z equal to 0, but then any plane of the form z equal to a constant is parallel to xy coordinate plane, right? So what you do is, in the given equation, you put various values of z and you see what the curve is. And that curve will tell you the entire, now you join pieces together and then you see what the entire surface is. That's the standard procedure of plotting a quadric surface, and this method is called, these curves are called traces or cross sections of a surface. Okay, so these cross sections are very important to be able to build the entire quadric surface. So let us look at a few examples of cylinders. So remember, in cylinders, one of the variables is missing, right? So in the first picture, in figure 1, we are plotting the surface z equal to x square. So z equal to x square is which form? Let me go back. Z equal to x square is this form where a is equal to 1, b is equal to 0 and I is equal to minus 1. In which case you will get z equal to x square. So this surface is called a parabolic cylinder for a good reason. So let us see why is it called a parabolic cylinder. So you all know picture of a parabola, right? So let us do one thing. So see, you don't see a y variable here, right? Which means that this surface, whatever picture you get, is same for all values of c when you put y equal to c, right? Because that is not going to disturb the equation. So let us put y equal to 0. Y equal to 0 means xz plane, right? So this plane that you see here, xz plane is y equal to 0. So when y is 0, what is this surface? This is a parabola, right? When you intersect it, when you put y equal to 0, you get a parabola. So z equal to x square. So what is z equal to x square? This is this picture that you see here, right? This is the parabola z equal to x square. All of you know the equation of a parabola y equal to x square. Now I've deliberately taken this example because we want to look at functions in R3 now, right? Surfaces in R3 now. So when you put y equal to 0, z equal to x square is this, and then what you do is you just look at this curve everywhere for all values of y. So you extend it in the positive direction of y and you also extend it in the negative direction of y. And when you do that, you get this entire surface, right? So this was very easy. So cylinders are very easy to plot because you don't see the third variable, right? So what you do is you take that third variable, put it equal to 0, plot the curve and then extend the curve in both directions of that missing variable. That's what we did here. Let us look at figure 2. In this figure, Z is missing and this is in the first form, that those two standard forms on the previous slide. So this is the first form. Z is missing, so you put Z equal to 0. When you put Z equal to 0, that's nothing but the xy plane, right? So on the xy plane, what is x square plus y square equal to 1? That's equation of a circle, right? So you draw this circle which is centered at origin and has radius 1. Then what did I tell you? What should you do? You extend this picture in the positive and negative direction of the missing variable, which is z. So you extend it in this direction and also in the opposite direction. In this picture, the negative direction is not drawn, but this cylinder is like an infinite cylinder, right? Whose axis is z. And this is the standard feature. If an equation is like this, you look at the missing variable, and missing variable is the axis that you get, right? About which you have this cylinder. Okay. This is figure 3, which is a different version of figure 2, where x variable is missing. So what do? You set x equal to 0. What is x equal to 0? It is yz plane. Now in yz plane, what is the equation? Y square plus z square equal to 1, which is a circle of radius 1 centered at origin. And then you extend this picture in positive and negative direction of the missing variable, which is x. So you get this picture. Right? So that's how you draw cylinders. You set the missing variable equal to 0. You plot the curve that you get and extend that curve in both directions of the missing variable. Okay, so cylinders are easy to draw. Now, when you go to quadric surfaces, you get various possibilities. Okay, so these are 6 possibilities that I have drawn. They're all in standard form. Okay, so if you look at the first, ellipsoid, cone, hyperboloid of one sheet and hyperboloid of two sheets. They are in the first standard form because you see x square, y square, z square terms everywhere. Whereas elliptic paraboloid, hyperbolic paraboloid, and these two are in which form? They are in the second form, right? Where you see x and y with squares and z with a linear term, right? And there is no constant term. So let me explain you a few pictures and then I will leave more discussion to the tutorial. So let us look at the first one. So what is the method that we discussed? Method of traces, where you intersect your surface with planes which are parallel to coordinate planes, right? Okay. So now if in this equation, this is an equation of 3 variables x, y and z. So suppose I put z equal to constant. So if I put z equal to constant, you can bring this term this side, and what you see is an equation of an ellipse, right? Similar thing happens when you put x equal to constant or y equal to constant. Even in those cases, you get ellipses, which means that when you cut your surface, when you intersect your surface with planes which are parallel to coordinate planes, you get ellipse. And the major and the minor axis depends upon what these coefficients you get, right? So the standard form of an ellipse is x square by a square plus y square by b square equal to 1. So you put it in the standard form and you see what equations you get, right? And you see that it's not an infinite picture in the sense that you have these end points, right? What are those end points? They are determined by, so let's say I put z equal to some constant. Okay. So if I put z equal to a constant, I bring this term here. So I get 1 minus that constant square divided by c square. So since the left hand side is non-negative, the right hand side should also be non-negative. So that poses constraints on what constant z can take, and that determines the limit of the values of z which are possible. And when A is equal to B is equal to C, you get a sphere, right? Because minor and major axes in all directions are the same. So you get a sphere. So this is for ellipsoid. And then let us discuss a cone. Now in a cone, you have various possibilities, right? Because let us look at horizontal traces. Horizontal traces meaning you cut in this direction, right? Horizontal meaning z equal to a constant. So again, when you put z equal to a constant, you get an ellipse, right? But here, unlike the first case, for all values of z, you will get an ellipse. That means it's a picture which extends in both directions of z, right? So you get ellipses like this. Now, when you take vertical traces meaning x equal to a constant or y equal to a constant. So if you put x equal to a constant, right, what do you get? You get a hyperbola, right? Because if x is a constant, you can bring this term this side and you will get a constant, right? If x is equal to k. But if x is equal to 0, let's say you don't have this term, you get z square by c square equal to y square by b square. That will give you a pair of lines. What are the pair of lines? Z by c equal to plus minus y by b. Those are the lines that you get. So you get these lines, you get these ellipses, and you get hyperbola, right? So if you intersect a plane like this here, you get one piece this side and other piece this side, which is a hyperbola. So that's how you see it. Okay. So let me talk about one more picture. These two are interesting. I will leave this to you. When do you get one sheet? When do you get two sheets? So that's important. You look at the difference in signs. So here you have a negative sign on z term. Here you have negative signs on x and y terms. Let us look at elliptic paraboloid, right? Here your z comes with a linear term and x and y come with square terms, right? So now when I put z equal to constant, I get an ellipse, right? And when I put x equal to constant, then I get parabolas, right? That is why it's called an elliptic paraboloid, because on one trace is one type of traces are ellipses and other type of traces are parabolas, right? That is why it's called an elliptic paraboloid. So the names are because of the traces that you see, the kinds of traces that you see, okay? And cone is called a cone because it looks like a cone, okay? So now let us, now I'm going to move to graphs of functions. This is important because you all are aware of how to plot a function y equal to f of x, right? A function whose y coordinate is a function of x, right? Now we are going to move to three variables, and when we move to three variables, we have to understand what's going on. How do you jump from two variables to three variables, right? So consider this equation y equal to x square, right? This is something really familiar to you. It's a parabola. So if you draw parabola in R2, this is x-axis, this is y-axis, this is the graph that you get, right? In R2. Now let me draw the same picture in R3. Now in R3, it is A cylinder, right? Because the z variable is missing. So how were we plotting cylinders? Z variable is missing, so you put z equal to 0. Z equal to 0 means xy plane. In xy plane, you draw y equal to x square and extend it in both positive and negative directions of z. So this is what you get, right? So now you see the difference. The same equation can be thought of as an equation in two variables, but can also be thought of as an equation in three variables. In three variables, you no longer get a curve, but you get a surface, which looks like this. It's a cylinder in this case, right? So in R2, we get a parabola, whereas in R3, we get a parabolic cylinder. Cylinder because of the definition of cylinder, that one of the variables is missing, and parabolic because you see parabola as cross sections, as traces. Okay, so keep this in mind. It's a very important concept that you can look at the same thing in R2 if you only have two variables, and you can also look at it in higher number of variables. Okay, so let us now define what a graph of a function in space is. So let U be a subset of R2. The graph of a function f from U to R, which is a function of two variables. So now we are moving on to functions of two variables, is the set of points in R3 x, y, z, where x comma y is in the domain of the function, which is U, and z is equal to f of x comma y. It's the value of the function. So if you look at the same thing in as a function from R to R, then you don't have z, you have y, and y is equal to f of x. So we are just imitating the definition, right, that we see in R2. Now when you look at this collection of points where x and y are in the domain, and the third variable is the image of x and y under f, you get a surface in R3, right? So the graph of such a function is known as a surface in R3. So if we look at this picture, this is the graph of the function z equal to fxy equal to x square. Now y is missing, right? So it's again a cylinder, z equal to x square. So what do? You put y equal to 0. Y equal to 0 means xz plane. In xz plane, you get a parabola extended in both directions. So this is the graph of the function z equal to, graph of the function fxy, which is a function of two variables, and it's a surface in R3. Okay. So now let us move on to level curves, which are very important to understand uh, graphs of functions which are in two variables or three variables. Okay, so we will look at two concepts. First is level curves, other is level surfaces. So let us first understand level curves. So let U be a subset of R2 and let f be a function from U to R of two variables, and let us take C as a constant. The set of all points x and y in the domain such that the value of the function is C is called a level curve of f with value C. Okay. This can also be thought of as the intersection of the graph of the function f with the plane z equal to c, right? Because z is equal to fxy. So let us look at this graph. This is the graph of function fxy equal to x square plus y square, right? So now what are level curves? Level curves are when you put z equal to a constant. So z equal to constant meaning plane which is parallel to xy coordinate plane, right? So you imagine chopping off your or intersecting this whatever surface it is, we don't know a priori, with the plane z equal to a constant. If you put z equal to a constant, if z is positive, you get a circle, right? So we have drawn several level curves here corresponding to z equal to 1 square, z equal to 2 square, z equal to 3 square, z equal to 4 square. And these are the circles here that you get, right? When z equal to 0, you get a point, right? So x square plus y square equal to 0 if and only if both x and y are 0. So you get a point. And when z is negative, when you put the constant to be negative, then you have no solution, right? Because x square plus y square is always non-negative. So how can it be equal to a negative number? So therefore this picture you see is only on the positive side of z. It is not there on the negative side of z. Because z cannot take negative values. It only takes non-negative values. So level curve of f at c for c greater than 0 is a circle. For c equal to 0 it's a point, and for c less than 0 it's empty. There is no level curve that you get. So by putting these level curves together we can easily build this entire graph of the function, right? So this is a very useful technique. These level curves are useful technique uh, to build the entire graph of a function. Now, why are these level curves important? They are useful. So this is just one example. They are useful for mountaineers and weather experts weather experts to draw isotherms, the curves on which the temperature is the same. Now, in this picture, we have drawn contour or plot of a hill, which is this B. So suppose you have a hill, okay, imagine this as the z axis, you intersect this with z equal to constant. So when you intersect the hill with a particular height, you on the plane, on the base, you draw those curves, okay. So when you are at the outermost, your height is minimum, right? And as you go in the xy plane, your height is maximum, right? That's what you see here. So when x and y values are really close to this point, your height is large, right? That's where the peak is. And as you go out in the xy plane, your height decreases, right? That's how it. So drawing these level curves for or contour plot of a hill helps the mountaineer decide the how the hill will look like as they climb or as they hike. Okay, so that is why level curves from physical point of view are in real life are important. Now let us look at a level surface. Okay, so what is a level curve? You look at a function of two variables, right? Now you look at a function of three variables. So let u be a subset of R3. The graph of a function f from u to r, which is a function of three variables x, y, z, is the collection of all points x, y, z, comma w in R4. So you have to go to one higher dimension, right? When you have a function from R to R, you plot it in R2. When you have a function from R2 to R, you plot it in R3. When you have a function from R3 to R, you have to plot it in R4, right? That's what we are doing here. Where x, y, z is in the domain, and this fourth variable is nothing but the value of the point, value of the function at the point x, y, z. Okay. Now we are not used to plotting things in R4, right? So The graph of such a function is in R4 and hence difficult to visualize. Therefore, one studies level surfaces for functions of three variables. What is a level surface? It's the collection of points x, y, z in the domain, which is a subset of R3, such that fx, y, z is a constant. This is called level surface of f with value c. So you put the final one as a constant. You look at this equation fx, y, z equal to c, and that is the level surface of the function with value c. So you have reduced your problem to R3 now, right? So because we can't visualize things in R4. So this is a very simple example. We will discuss more examples in the tutorial. This is a very simple example of level surfaces of a function. So we are looking at the function fxyz equal to x minus y plus z plus 2. Now, if you put this function to be a constant, you get equation of a plane, right? So level surfaces of this function are nothing but planes. So you see these planes here for various values of constant c equal to 1, c equal to 2, c equal to 3. So when you put, let's say for example, if you put c equal to 2, you get x minus y plus z plus 2 equal to 2, which gives you x minus y plus z equal to 0, which is a plane that passes through the origin. That's this plane that you see. And as you vary your values of c, you get other planes, right? So what will happen? When you vary these constants, you get planes which are parallel planes, right? Why are they parallel to each other? Because their normal vector is not changing. What is changing is the constant term. Normal vector still remains 1 comma minus 1 comma 1. That is why this picture looks like this. So you get, for various values of c, you get these planes, all of them having their normal vector as 1 minus 1 1. Therefore they are all parallel planes, right? And actually these planes fill up the entire R3, right? So let me stop here. We will look at more examples in the tutorial.